Alright guys, good morning. This is about lenses and ray diagrams. So we drew out the ray diagrams for curved mirrors. My sort of assumption is that we don't really need to go through the ray diagrams for lenses again exactly the same way we did. The process is super similar. But let's start with how lenses create images. So the first thing we need to know is that a lens is made out of a material that's plastic or glass, and therefore it bends light when it changes mediums. And what's interesting is that it actually happens twice. So the light comes in, it hits, and it bends, and then it hits again on the other side and it bends again. That's kind of annoying, and so to deal with it twice and it kind of messes things up. So we actually generally use what's called a thin lens approximation, which is the assumption that if the lens is thin enough, then we can approximate as just bending once here. So most of what you're going to see the rest of this way is we're going to assume it just bends at the very midpoint of the lens. Okay. All right. So a converging lens. So this is a lens like a magnifying glass, and you can see the big thing here is these light rays. They come in and notice how they're parallel to one another. Okay. And when they all come in, they hit the lens. And this one actually does show it bending twice, but really, again, we're not going to do that generally. They all bend. They all meet at the focal point. Okay. This is the sort of thing that you would do if you were trying to set something on fire with a magnifying glass. You'd want to take all of the sun's rays, and then you'd want to put the magnifying glass so that they all met right on top of a piece of the paper or grass or stick or whatever, leaf, whatever you're trying to burn. Okay? And that's because then all of the light is being concentrated to a single tiny point. And that's how you get enough energy and heat to heat it up. Now, this only can be done with the sun. Why can't it be done with a regular light in a room? And the answer is because the light rays from the light of the room aren't parallel enough. The sun is far enough away, they act as if the light rays are essentially parallel to one another, so you can focus them to a very small point. Light from a lamp in your room, not parallel enough. But again, so this is the converging lens. We have a focal point over there. The diverging lens bends the other way. So you can see it hits, and again, we're showing double bend here, but really bend, and it bends up. And so they are spreading out. That's why it's called diverging. The light rays spread out. That means the focal point is again where it looks like they all came from. So we track it back, and it's behind the lens. It's on the same side the light's coming from. So that's the big difference in how the focal points are used. All right, so the ray rules. Incident light rays coming parallel to the principal axis refracts through the focal point. Incident ray coming through the focal point refracts parallel. All right. This last ray here we're never going to use. We don't need a third ray. We only need two. So we're just going to use those first two. All right. And then this is the dotted lines backwards from the refracted ray, because this is when the image might appear behind the lens. This is the big difference between mirrors and lenses. Mirrors, right, the light hits it and bounces back towards you. And so light on the same side as the object was real and considered positive. It's the other way for lenses, because light naturally goes through the lens, and so light on the other side of the lens is considered images on the other side of the lens are considered real. Okay? So a virtual image, like a real image, is the kind of thing where you could project like a slide projector. You've got slide, lens, and the image appears on the wall, and you can see it on the wall. A virtual image, the only way to see it is to look through the lens. So this is like a magnifying glass. You don't hold the magnifying glass and then see the image up there. You hold the magnifying glass and you look through it, and that gives you a virtual image. Okay, so for converging lens, we use the focal point on the opposite side, as you saw, right? Because that's where the light rays converge. And for a diverging lens, we use the focal point on the same side. All right, so again, this is how we do it, right? We would say we're going to take the, I don't know, I showed two of these, but we're going to take light from the top here. We're going to draw it parallel to the principal axis, and then it's going to refract through the focal point. And light from that, it's going to refract through the focal point on the same side, and it's going to go that way. Same here with the green, and then we get essentially the pencils flipped upside down, because the bottom of the pencil is going to appear here, and the top of the pencil is going to appear here. So that means it's going to be upside down. All right, so the basic options here. Oh, I forgot to write this out. So what? That's okay. You can figure it out. If the object is beyond two focal lengths behind it, so we go parallel to principal axis, through the focal length, parallel to principal axis, we get this little arrow. It's upside down, again, because the base is always going to be on the principal axis. Location is between F and 2F. inverted, smaller. This is a real image. Again, it's on the opposite side, so it's a real image. Same deal. Location is about at 2f, right? Again, I've talked about how this isn't perfectly measured. Should be about 2f. The orientation is up inverted, size is about the same. Image again is real. Third one, right? Same set of rules. The location is beyond 2f. Orientation is inverted, size bigger, image type real. This is the projector. If you want to use a slide projector, what you have is like a little small slide, a lens. You put it close to the focal point, a lens, and it appears bigger on the other side, but upside down. So that's why you put slides in it backwards. Excuse me. Huh. All right, but what if it's close to the focal length? So here's the one we did, right? So we go in and we line this up with the focal length and the center lens, but we draw it up, and then it goes parallel. And here, right, we go parallel in, and it goes through the focal point on the far side. So again, if you're observing these two rays, where does it look like they came from? It looks like they came from here. Okay. And so this object is going to be bigger, inverted. It's going to be behind the object. The best way to describe this image is it's behind the object. It will generally be closer than f, but that's not really the point. The point is it's got to be behind the object. This is a virtual image. This is the magnifying glass, right? You hold it over something, and you look at it, and you should see a larger image of it. And finally, the concave lens. Okay, these lenses are actually what's used for glasses most of the time. Right? Most nearsighted people have this kind of glasses. So when you're looking through glasses, right, you are always looking through the lens. So it's got to be a virtual image. And if you've ever done like this, where you hold it like this and then go like that, especially if you hold it a little bit away from your eyes, you can see it always is smaller. Okay, it always makes the image much smaller than the actual object is. So again, we go in parallel. This time we use the same side focal point, and it bends up. And when we're going we go to the opposite side focal point, and that's what makes it go parallel. And we track them back, and we get this little image here. Location is between the object and the mirror. The orientation is upright, size smaller, image type. This is a virtual image. Okay. So again, this is very similar to the process by which we did mirror ray diagrams. Okay. Next up. All right, so this is sort of like a summary of all that, right? For diverging lenses, it's always virtual, smaller, upright. Right, here are the deals. Object location outside 2f, between 2f and 2f, it's inverted, etc., etc. You can copy down, pause the thing, copy down, whatever. Good news is the equations are basically the same. 1 over f is 1 over dl plus 1 over di, and magnification equals h over hi over ho, the height of the image over the height of the object, negative d of the image over distance of the image over distance of the object. The big thing is that f is negative for diverging and positive for converging. And I should also add, di is negative if it's on the same side of the lens as the object, and it's positive if it's on the opposite side of the lens as the object. So that's the reverse of mirrors. Mirrors, same side was positive, same side as object was positive. For lenses, opposite side of object is positive. All right, we got 3 examples. We're going to project a 2 meter tall image of a 10 centimeter slide on the wall. What kind of lens should you use? You have 2 lens options. It either has a positive or negative focal length of 20 centimeters. Okay. So how far from the wall should you place the lens? All right. So this is a projected image. That means real. That means it must be a converging lens or a convex lens. That means we got to have the positive 20 centimeter lens, right? Okay. And then how far from the wall should you place the lens? That's what we're going to do some math for. Right, so projected image is real image, converging lens. Please note, this is an inverted image. Has to be. That's really important because it's going to tell us that the actual height of the image is -2, not 2 meters. Okay? And the height of the object, though, is still 0.1. So we have 2 equations. This is a 2 equations, 2 unknowns thing. Well, I guess only one unknown we have to find. But we have 1 over f, 1 over dl plus 1 over di. 1 over 0.2 equals 1 over di over 20. Oh, right, that's 20. I was trying to remember what 20 again, but it comes from over here. Right, we do this part first. Magnification is negative 2 over 0.1 equals negative di over do. So then we have 20, which is, I lost the negative signs, right, because they're negative on both sides, cancels. So this is 20 equals di over do. So that means do is di over 20. Put it in there. Okay. 1 over di over 20 is actually 20 over di. So 20 over di plus 1 over di. That is 21 over di. Multiply both sides by di. At 5 di equals 21. Distance of the image is 4.2 meters. So that's how far the lens needs to be from the wall for the image to be in focus. Okay. 2 more. Using a concave lens with focal length of negative 50, you see a person that appears to be 20 centimeters behind the lens and 1 meter tall. How tall are they actually? Okay. So 20 centimeters behind the lens. So if you're looking through a lens, that means the image is behind the lens. That means it's on the same side of the lens as the object. So this 20 centimeters is going to be negative. Right? So we have f equals negative 50, di is negative 20, hi, the height of the image is 100 centimeters. 1 over f equals 1 over do plus 1 over di. 1 over, that means 1 over negative 50, I'm leaving everything in centimeters this time, equals 1 over do minus 1 over 20. 1 over 20 minus 1 over 50 equals 1 over do. Do is 33.3 centimeters. Okay, so it's a little bit further behind there. And remember, do is always positive, no matter what. Okay. The height of the image over the height of the object is negative di over do. We plug in, we get a height of the object is going to be 167 centimeters. All right, here's where things get a little tricky. 2 lenses. Okay, we got an object. You'll see a drawing on the next page. You got an object, then you have one lens, a diverging lens, then you have a converging lens, all in order. And I want to know where the final image is. So when you ask, why is there a final image? So light is traveling from the object. Well, let's just go to the next page. Light is traveling from the object. It's bouncing off that. It's going through the first lens. It's then going through the second lens. The second lens does not get light from the object unless that light has gone through the first lens. Okay, so the object, what the second lens sees, and I use sees in a very loose term, the light that comes to the second object seems like it's originating from the image of the first lens. So the image of the first lens is the object for the second lens. That's what we get here. So like we know this is a diverging lens, so we know that the first image is going to be smaller in between the object and the lens, and that becomes the object for the second lens. So DO2, the distance, the object distance for the second lens, is we're gonna have to find that by figuring out where DI1 is. Come back to this image again on the next screen when I'm doing this. Okay. So for the first lens, right, it's 1 over f1, negative 10, 1 over do, 1 over 20, plus 1 over di1. Solve this, we get di is negative 6.67. That negative sign, it just means it's on the same side, right? It just means this is 6.67. So how far is DO2? Well, this is 20. This is 6.67. So the DO2 is 26.7. Now, notice, it's not 13. It's really easy to say, oh, it's 20 plus negative 6.67. But that's not what's happening here. Negative 6.7 is the negative is a direction. So 6.67 is that way. And that means that the total distance is 6.67 plus 20. So 1 over f2 equals 1 over do2 plus 1 over di2. Okay. We do this, we get an answer, 34.23. I didn't really work out the math for that because it's just a bunch of decimal stuff. Okay. Double lens problems are a little tricky. Okay, we'll do another example at the beginning of class on next week because when we talk about glasses, remember that's what glasses are. You have a lens in your eye, and then you also have a lens of the glasses. So those are essentially double eye problems. Okay. All right, so that's how you do lenses, how you figure out where the image is formed by them, and yeah, good luck on the homework.